So what resolution is high enough then? So let's think about this for a minute. For example, let's say this is a structure we're trying to image, some sort of fiber or cell walls. And we're going to think about the voxel size first. The voxel size is the size of box you're going to use to sample this structure or image. And if you use too large of a voxel size, your image might look like this. You can't even see what kind of structure you have there. But if you use a small enough of a voxel size, you can get an image as the structure looks like. And in this example, let's say we're going to look at a relatively small or narrow part of this structure, and it's 2 microns in size. And if you want to see this 2 micron feature, your voxel size needs to be at least half of it. Ideally, you want that to be 1/5 to 1/10 of the size of the feature you're trying to resolve. But at least just to see that it's there, that voxel size needs to be at least half of the feature size. So let's take a look at the actual CT cross sections and see what happens if the voxel size is too large. So this is a cross section of a foam material, and this was collected at 2.12 micron voxel size. And there should be a polymer wall separating 2 cells there, but you can't even see that it's there in this image. If you use about 1 micron voxel size to look at the same thing, now you can kind of see that there is a little line there. If you go down to about 1/4 a micron, then you can clearly see that there is a polymer wall between 2 cells. Let me zoom in. So there is the wall, and you can see a profile here, and there is clearly a gray level peak, and you can even measure the thickness of this wall. And for this sample, the thickness of this wall turned out to be 1.9 microns. And if you use 2 micron voxel size to see this, you're going to miss it, and you can't even see that it's there. So to summarize, if the size of the feature you're trying to resolve is, for example, 5 microns, the voxel size needs to be at least half of it. In other words, you need at least 2 voxels to sample that area and see that that feature is there. Ideally, you want that to be a little bit smaller, something like 0.5 micron to 2.5 microns. And this is just the voxel size we're going to use for sampling. But if the resolution function that's coming from all the hardware pieces on the X-ray CT scanner is a lot larger than the voxel size, then this resolution function is going to blur the image. And no matter how small of a voxel size you choose, you cannot resolve this feature. Everything gets blurred. So it's also important to make sure that the resolution function size is comparable to the voxel size you're selecting. Now, what determines the resolution function? The resolution function depends on the X-ray focus size and the pixel size on the detector and the overall geometry. For example, if this is the focus size you're using, and if it's drifting, that drift needs to be taken into account as well. And let's say the overall defocusing coming from the geometry is about this size. And you have the pixel size on the detector. Technically, you can calculate the resolution function just by convoluting all of them together. But practically, it's actually easier to measure the resolution. You can measure what's called spatial resolution. And the spatial resolution is related to both the resolution function and the voxel size. And this spatial resolution more or less tells you the smallest feature size you can resolve with the setting you're using. So this is something you can measure or test. But how do you test this resolution? So there are tools you can use to do this. This one is called Micro CT Bar Pattern Phantom by QRM. And it's just a little piece, probably about an inch in size. And this piece has line pairs varying from 5 to 150 microns, laid out like this. And you can do a CT scan of this little piece and see how small of a line pairs you can resolve. And the smallest line pair you can resolve is essentially your spatial resolution. That's the smallest feature you can resolve. If you need to test a resolution below 5 microns, QRM makes this nano bar pattern as well. And this one has 1 to 10 microns line pairs laid out like this. And this is an example of a CT scan tested on the nano bar pattern. And this image was collected at 2.2 micron voxel size. At this voxel size setting, you can easily resolve the 8 micron line pairs. You can see 6 microns, no problem. And you can see 4 micron line pairs as well, but you can kind of see that you're approaching the limit of what you can see with this resolution. And this makes sense because 4 microns is about double of the voxel size 2.2 microns. So this is the smallest feature you can resolve with this setting. And the fact that you can see 4 micron line pairs with 2.2 micron voxel size means that the resolution function size is comparable to the voxel size. So this is for micron level resolution. If you need to test something less than 1 micron, you can use this resolution chart by JIMA. This is only for 2D measurement, but it has line pairs from 0.1 to 15 microns. And this is a 2D measurement example on the 0.6 micron line pairs. If you zoom into this area, you can see that the 0.6 micron lines are resolved. And this image was collected with 0.27 micron voxel size setting. So again, you're seeing something about double in size of the voxel size. And this means that your resolution function size is comparable to the voxel size. So this is how you can test the resolution, actual resolution you have on the system you're using. And it's important to achieve high resolution and make sure that you have the resolution you need to get high quality images or to make your images look better or pretty. But it is also important for the quantitative analysis. So how does the resolution affect analysis results? So let's take a look at an example of a foam analysis. So this is a piece of a heat insulator, just like the insulator people use in the walls of houses or buildings. And the porosity is an important parameter for heat insulators because you need to increase the porosity to have a lot of air in it to make it work as efficient heat insulator. So let's say that we want to measure the porosity of this foam. You can take a small piece out of it and do a CT scan. And if the resolution is high enough, you will see very, very thin polymer walls clearly. Then you can do the image segmentation for pores or cells and the polymer part and calculate the porosity. And it came out as 96.7% for the sample. So this is all good. But what happens if you change the voxel size and you use larger voxel size or lower resolution? This is what happens. Those are the different voxel sizes we use to scan the same sample. And those are the calculated porosity values for different images. When you use 0.53 or 0.63 micron voxel size, and that is about a quarter of the feature size we're looking at here, you can get consistently the same number, 96.7% as the porosity. But if you continue to increase that voxel size, the calculated porosity starts to increase as well. So now your quantitative analysis result is changing. This happens because when the voxel size is small enough, you can see the polymer cell walls and segment those voxels. But if you use too large of a voxel size, then those walls start to disappear and you start counting those voxels as air or pore by mistake. And that is why the calculated porosity can change. So achieving a high resolution, as you can see here, is important to do quantitative analysis accurately.